In this video, we're going to factor special products. Specifically, we're going to factor special products that take these three forms. This one's called the difference of squares, and I would write down these names. This one's called the difference of cubes, and this one's called the sum of cubes. I think those names are pretty self-explanatory. Difference means subtraction. Sum means addition. Let me go back to this slide. And so what we're going to do is we're going to look at binomials. We're going to see which of these three forms it fits, and then we'll instantly be able to factor it. Because anytime you have a value or a polynomial in one of these forms, the factors will always take this form on the right. So I refer to these as recipes. So it's kind of like we got our finished cake over here, and we're saying, okay, what ingredients did we put into it? It must have been those. Okay, so if I'm going to use layman's terms, that's how I might refer to it, as a recipe. And so whenever I'm looking at this first example, if I'm looking at x squared minus 25 down here, I'm looking out of my three examples up top, it looks a lot like that one. It looks a lot like a squared minus b squared. And if it does take that form, our factoring will be easy because we can just factor it as a plus b times a minus b. And so the question is, for this polynomial right here, this binomial, the question we're asking ourselves is, what is the a value and what is the b value? Okay, so whenever I look at it, for this one, the a value is just this first term. Our a value is just x for this particular problem. And when I look at the b value is some number squared. Well, that value squared is a 25. So you're asking yourself, what value times itself gives you 25? And hopefully you're saying that's a 5. So that would mean our factored form here, it's going to take kind of the same structure. But instead of a, we've got x, and instead of b, we have 5. So it's x plus 5 times x minus 5. You could get to these factors by doing your long factoring process that we've learned. But just know that if it takes a form, you don't have to. The difference of two squares is kind of like a shortcut. The square root of the first term, the square root of the last term, you add it once and you subtract it once. Let's do another example. Now, we've got another problem. Here's our problem this time. Once again, this is something squared minus something squared. This is another example that fits this first recipe. This is another difference of squares. And so I'm going to copy our recipe down below it. I like thinking of it that way. It's helpful for me. A squared minus b squared equals a plus b times a minus b. And so we're just asking ourselves, okay, well, what is our a value in this situation and what is our b value? And so if I look at the a value, we're saying, okay, some number squared gives you 4x squared. So we're saying, what times itself? What is our a value if that times itself gives us 4x squared? And hopefully you were saying 2x, because 2x times 2x is 4x squared. In other words, like I said in the last slide, it's basically the square root of whatever this term is. So we've got a 2x and a 2x. And now we're identifying the b value. What number squared gives you 36y squared? What's the square root of this? And hopefully you're saying, okay, well that's just 6y. So we have 2x plus 6y and 2x minus 6y. This would be our factored form. You could multiply those back together with FOIL or the box method or distribution, whatever method you choose, and you should end up back at this. Let's do another example. So notice for this one, we're not squaring anymore. We're not doing a difference of squares, but we still have a difference. But we have a difference of cubes. We have something to the third power and something else to the third power. Okay, so I'm going to copy down that recipe. That's what we're going to be dealing with this time. So we have, if something cubed minus something cubed, then it's going to be, and I'm just copying this down exactly as it appears, it's going to be a minus b times a squared plus ab plus b squared. Now let's see if we can use this recipe up here. So first off, you say, okay, what's our a value? What's the cube root of m cubed? In other words, if a is being cubed and here m is being cubed, well then your a value is just going to be m. And we can fill in the blanks. Looks like we got an m there, an m there, an m there. And I'll go and fill in all the other stuff. Okay, now let's figure out what the b value is. I'll kind of be color-coded because this recipe is a little bit more complicated. For our b value, we're saying, okay, what number cubed gives us 64n cubed? Well, we know there's going to be n in it, but what times itself 3 times gives you 64? What times what gives you 64? And that's going to be a 4. That means our b value is actually going to be 4n. Now I realize it's not the cleanest representation, but basically we can just simplify this whole thing. So let's take it a step further. We have m minus 4n times m squared. Now we got to look at this middle term. How do we simplify this? Well, we just rewrite it in a different order. It's just m times 4 times n, which is often written as 4mn. And then lastly, 4n squared would be, okay? And so this would be our final factored form of that difference of cubes problem, okay? Identify what A is, identify what B is, and then fill in the blanks in your recipe. Last example. Now, we have a sum in this situation, so you can tell it's going to be sum of cubes. Now, when I look at that, I'm going to copy down our formula first. We have A cubed plus B cubed equals A plus B, and then we've got so we're starting with the same questions, okay? What value cubed gives us 8q to the 6? So what times what times what gives you 8q to the 6? And this is a little bit trickier to find this, but we know that 2 times 2 times 2 is 8, and that q squared times q squared times q squared would give you q to the 6. So through all that, we find that our a value is going to be 2q squared. Basically, it's the cube root of this first term. That's what a is. And now let's look at our b value. For our b value, okay, we're looking for what times what gives us 125 p to the 9th. And if we look at like two separate problems, we can look at the coefficient first, and we know that 5 times 5 times 5 is 125, and then p cubed times p cubed times p cubed would be p to the 9th. We know that because when we multiply these values with the same base, we add the exponents. So if a is 2q squared, we know that b is 5p cubed. Now, hopefully I don't get too messy trying to fill in the blanks up here in my recipe. I'm hopefully going to make this easy to understand, but let's get started. So I'm going to start with the a value. I'm going to try to do it in red. So we have a 2q there. 2q squared, excuse me. And then coming over here, we have another 2q squared minus 2q squared times some b value. And then now let's fill in then we'll add the b's. So our b value is 5p to the 3rd. So our b value is 5p to the 3rd. Here, I'm kind of running out of room, so I'm going to squeeze it in there, 5p to the 3rd. And this is going to require some simplification here in a second. And then lastly, we have 5p to the 3rd squared. Okay? And now let's simplify. I'm just going to move over to the right. I don't think that these first two terms in the initial binomial don't need any simplifying. So we have 2q squared plus 5p cubed. And we have 2q squared. Now here's where we got to simplify a little bit. If I'm multiplying 2q squared times 5p cubed, the 2 times the 5 gives you a 10. And then q squared times p cubed is just that. And then last term, we are almost done, is going to be 5p cubed squared. So 5 squared is 25. And here when you raise a power to another power, you multiply exponents. So that would be q to the 6th. This is our factored form of that last trinomial. Once again, easy to get overwhelmed when you look at the whole thing. See which recipe you're using, identify A and B, and then fill in the blanks.